Hello students, so today we will continue our lectures on computational fluid dynamics and we will discuss about using this same scale, this cloud computing tool in solving some problems. So the first problem that we will take today is called turbulence cancellation. Now turbulence is the is the drift faced by an aircraft while it is moving. So we can see that there are two cases. The first case on the left, this one is where there is little or no turbulence. So from the plot you can understand the plot here, whereas the one on the right is where a very high turbulence can be seen. Now what is observable is that this aircraft here, it is deviating from its mean position, right? So that means it is getting some sort of upward thrust while it is traveling, and upward drag while it is traveling. So this upward drag has to be minimized if one wishes to achieve some turbulence stability, especially the commercial aircrafts. Now, the turbulence cancellation is basically based upon two things. First is the DLC, or the direct lift control. By direct lift control, it is meant that the variation of the dynamic lift and very with low inertial flaps present. Now, what it is based upon a real-time monitoring by the pressure by flaplets at the trailing edge. Okay, so we will see what does this flaplets mean. And another aspect of turbulence cancellation is to have an holistic flight dynamic integration. That means the acceleration, the pitch, the roll, and the wing movement, one should have a holistic integration of all these factors. So then only this turbulence cancellation can be achieved. Now, one of the ways of having a turbulence cancellation is to have a laminar flow wings. Laminar flow wings means to have a curved wings with the thickest section, uneven distribution of the mass. That means the thickest section at 50% back side. Okay. Now this again, if you compare it with the conventional wings, what can be found is that conventional wings are 20% behind the main mass, or the whereas the this commercial, I mean this laminar flow wings, they have designs as that this is the point of attack. Point of attack means the point or the region of the wing where the pressure due to the wind or due to the air is the maximum. This is the attack point. Now from this point one gets an upward lift, and also one gets one drag, and actually this is the result. So this is the lift, this is the drag, this is the result. Now if we have a combination of mass distribution, like one in case of a thicker film, then what we can reduce the drag, because we are having a disproportionate mass causes a reduced drag. Now, another way of achieving mass turbulence stability is by using winglets. Winglets are nothing but vertical extensions from the wing end. Okay, so these winglets, they reduced the vorticity. Vorticity means the rotational the rotation that one can have when it is moving through a fluid. And we can also have rivulets. Rivulets is grooves. Rivulets comes from the word rib, and that is grooved onto, and it is mainly done to reduce the friction drag. Groove on the surface of the wings. Then we can also have some vortex generators on the wing surface, which are basically small fins or wings. And lastly, we can also have a porous wing structure. Now, having a porous wing structure affects the turbulence as the following force components, like the lift coefficient, the drag coefficient, the pitch movement, the lift versus drag, the gradient of lift, and aerodynamic center with respect to angle of attack. They are all the function of porosity. And by lift coefficient, mathematically, we can express the lift coefficient as the lift force, which is L divided by half rho v square S, where v is the speed of the air or the aircraft moving, S is the spacecraft area, A is the air density, and L is the force. Now, the lift generated by an airfoil or wing is related to the dynamic pressure of the airfoil. Now, this AO stands for angle of attack. So up to 15 degrees, increase in angle of attack means increase in CL. And the airfoil shape also is very handy, because we have a cambered shape, that means a curved shape, that is valid for subsonic aircrafts, that is low speed aircrafts, whereas the one with where we require very high speed, that we need jet aircrafts, there we need to have this CL low, and there is an increase in speed. You can see that this CL is inversely proportional to this V. So the higher the speed is, the lower will be the CL. The airfoil types, there are different airfoil types. One can have a flat airfoil type, and correspond to that we can have a different flaps. So you can see that with the flaps, the lift coefficient is high, and this is what is required. Now, the commercial Boeing 747 aircraft, it uses lift wings, high lift wings, to increase this CI. Now, for the wing optimization for turbulence, this is the shape of the airfoil that was designed through SimScale cloud computing. And what we can see is that there are some flaplets at the trailing edge, and these flaplets, they are controlled in real time by sensitive pressure sensors, and the feedbacks are controlled to the servo motors. And the reason why these flaplets are kept is that this flaplets decrease the upward draft, controlling their movement. And this is pressure and velocity distribution surrounding that flaplet. And this trailing wedge flaplet, it deflects upward to cancel the draft. So it is the draft itself moves away, the flap itself, to transfer the draft. And this is how the velocity around the wing of decreased air draft looks like.